So it's our great pleasure today to have Matthieu Geist, who's a full professor at the University of Lorraine in applied mathematics. And since 2018, is also on second attachment at Google Brain Paris as a research scientist there. And his research interests include machine learning, and in particular, reinforcement learning and imitation learning. So it's a real pleasure to have you there, and the floor is yours.
Thank you. I will maybe cut my video because I have a bad connection. And today I will talk about regularization in reinforcement learning. And the first part of the talk will be a warm-up to do some recall about DQN and approximate value iteration. But given the previous talk, it will just a matter of giving some notations. And then we'll talk about regularization in reinforcement learning, show some case study with notably Entropy and Kullback level regularization. And we will also see some theoretical results and why it is interesting to do regularization. So first, as a warm-up, you all know now that reinforcement learning is a closed-loop control problem, where the agent observes the reward and want to maximize the cumulative reward over time. And the control is learned from data. Usually you don't know the model directly. And it's formalized with Markov decision processes. So I will write big S for the state space, big A for the action space. A policy pi, in my case, will be stochastic. It will be quite important. So when you work with DQN, you can only consider deterministic policies because you know that the optimal one is deterministic. But when considering a regularization, we will need stochastic policies. So for a given state, the policy gives a distribution over action, and you sample according to this distribution to know the next action to apply to the system. But the rest of the definitions are the same. You just replace the reward of state action by the expectation over action given the policy of the reward. And for computing the optimal policy, you can do dynamic programming and notably value iteration that I will present a bit later. So the Q function will be convenient. So you've seen a lot about Q functions so far. I just write them like this. And you have the well-known Bellman equation that says that the Q function in a given state action couple is the reward plus gamma, the expected Q function in the next state action couple, with an expectation according to the next state, knowing the dynamics, and an expectation on the next action given the policy. And the Q function of a given policy is a unique fixed point of the Bellman operator T-pi that will be very useful in the following, and that we will modify a bit. So this is value iteration that you should know. And you have an important concept in reinforcement learning. It's the concept of greedy policy. If you have a Q function, you will take a policy to be greedy according to this Q function. If you put a probability of 1 for the action that maximizes the Q function for this state or 0 else. And this is at the core of many reinforcement learning algorithms. And this is the thing that we will modify with regularization. And so you can write value iteration as follows. You have two steps. The first step is the greedy step. Given a Q value, you compute the greedy policy. And the second step is the evaluation step. Given the new policy and the previous Q value, you update the Q value by applying the Bellman operator of the new policy to this Q value. And this is an abstract form of value iteration. But if you write it component-wise, if you use the fact that if you take the action, which is the Rmax that in amounts to maximizing the Q value, you have the classic value iteration equation, whereas the next Q value is the reward plus gamma, the expectation of the next state, of the maximum reaction of the Q value in this next state. And the question is, if you apply this algorithm, it will converge to the optimal policy and to the optimal Q function. But the question is how to use this to derive a reinforcement learning algorithm. And in reinforcement learning, we have a few problems. The first problem is that the model is unknown. That is, you don't know the transition probabilities and you don't know the reward. You can just observe samples from the system through interaction. You will learn from data and you collect this data. It's not a fixed data set usually. And the state action spaces are too large for representing exactly the Q functions. The state space usually is too large. The action space can be discrete, but it can also be continuous and require some approximation. So if we go back to the equation of value iteration, the unknown model says that we cannot have this expectation. We can only sample with usually only one single next state. The learning from data says that we cannot compute this update for any state action couple, but only for a subset of the state actions pairs. And the fact that the state action space is too large means that we cannot have a tabular representation of this Q value. We will need to have a kind of approximation, for example, with a neural network. So to go from value iteration to DQM, the idea is to replace each of these parts that we cannot handle with reinforcement learning by some approximation. So for the model being unknown, what we will do is that instead of taking the expectation, we will just sample. And the sample comes from the transition we have sampled and that we store in the data set, usually known as the experience replay buffer or whatever. This guy, we cannot compute it exactly because the state action space is too large, so we will adopt a parameterization. For example, a neural network parameterized by theta. Theta is a set of weights of the networks in this case. And we'll try to minimize the difference between Q theta and the bootstrap estimate of Q theta. Theta bar is a copy of the network or the target network. And as we don't have access to all state actions pair, we will optimize over only the available samples. So we have an empirical expectation over the data set that we currently have. And we solve for this least square problem, hoping for having a good approximation of the Q value. And if we do this sequentially, we will learn something which will be maybe a good policy by being really according to Q function. There are a few questions. The first one is how to fit the data set, and the usual way is to do it with interaction data. Another question is how to interact with the system, and beyond this, there's the exploration-exploitation dilemma, and there will be talk about this. But for now on, we'll consider simply epsilon greedy policy. So you play greedily according to the Q value with a given probability, and randomly with a smaller probability. And the question is also when to update the target network. If you do it too often, it will be unstable. If you do it not often enough, it will be too slow. So this is a choice to be made on the algorithm. And if you do all these things and you put them together, you end up with the DQN algorithm that Bilal presented extensively before. Now, I will come back to the approximate dynamic programming viewpoint. And for me, DQN will be this scheme. So this hides a lot of things, but this is quite practical to imagine new algorithm and to do the analysis. So the policy is still greedy according to the Q value, because if you have a Q value, be it a tabular representation or a network or whatever, you can compute the greedy action because you can enumerate actions. And then the evaluation step will be the new Q value will be the Bellman operator applied to the previous Q value plus some noise. And this is a random function of the state action space. And in this term, I put everything which is the difference between what I obtained by solving my least square problem with a deep network and what I would obtain by applying exactly the Bellman update. And the question is how this error will propagate through iterations. So you iterate this scheme by increasing k. At each iteration, you suffer from some error epsilon k, and what will be the error you suffer in the end. And you have this kind of bounds. So what you will bound is the distance to optimality. The distance to optimality is the difference between the optimal Q-value, the Q-value of the optimal policy, and the true Q-value of the policy that you compute with your algorithm. That is the policy being greedy according to the last estimate of the Q-value. And you will bound it by a term, which is a product of two terms and an addition of another term. So the last term is the bound when you have no error. When you do exact value iterations, epsilon are 0, so this term vanishes. And this is so the rate of convergence in the ideal case. And you see that the error will decrease in gamma per k, with gamma being the discount factor, so it decays quite quickly. And then you have a product of two terms. The first term is the horizon factor. So this is called the horizon factor because when you work in an MDP with in a gamma discounted setting, you can see this ever as I play with the MDP, and at each step I have a probability of gamma of continuing to play and of 1 minus gamma of stopping to play. And if I do so by considering non-discounted reward instead of discounted reward. So you can see a discounted criterion as saying I will play without discount, but on a random horizon. And this random horizon is generated according to a geometric law of mean 1 over 1 minus gamma. So you can really see 1 over 1 minus gamma as the average horizon of the optimization you want to do in your control problem. And for example, if you take gamma equal to 0.99, which is a classical choice, 1 over 1 minus gamma is 100, and the square of this quantity is 10,000. So this term can be quite big, but it's almost unavoidable. And it makes sense because you optimize over an horizon h. It's somehow normal that you suffer for h times the error you do at each step. And the last term is the error term, and it's a discounted average of the error you suffer at each iteration. But it's a discounted average of the norm of the error. This means that even if the error here has 0 mean, and it can happen, for example, if you have a tabular representation and the only error comes from sampling, that is, instead of taking the true expectation, you sample just once, value iteration will not converge. And these bounds tell this because you have a sum of the norm of the errors. So you cannot have a composition of the errors between iterations. And you will see later that this is something that regularization brings to reinforcement learning. So after this quick recap of what is DQN and approximate value iteration more generally, I will present regularized approximate dynamic programming. So what is regularization? You will see it in the many next slides. But basically, the idea is to modify the greedy step to be less greedy, but in a smart way. And next, the question is why doing regularization? And it has been introduced in many different ways in the literature from many different viewpoints. And the way I will present it is one of them. It's useful because it allows unifying many different approaches, but it doesn't provide explanation for everything. And for example, it arises when framing reinforcement learning as a probabilistic inference problem. So basically here you see, you can say that you have a kind of probability that would be proportional to that would be basically the softmax of the cumulative reward of trajectory. So you have a probability of trajectory, and you want to maximize the likelihood of this probability, which means maximizing the cumulative reward. And if you do so, you end up with some kind of regularization. It has been introduced to favor exploration, to smooth the optimization landscape. We'll see why also. to use kind of trust region to policy update. Instead of when you're greedy, you do very big step in the policy space, and it can be harmful. You can think of gradient descent, and the idea is to do smaller step in this policy space. It provides theoretical guarantees, and the thing is that it works very well empirically. Many state-of-the-art algorithms use some kind of regularization. So as I said, the viewpoint here will be that of regularized approximate dynamic programming, which allows for theoretical analysis and recovering many, if not all, existing agents from a common viewpoint. So I will introduce some notation. And for example, instead of writing the expectation of the Q value according to the policy, which is a sum over action of the policy of the probability of the action times the Q value of this action, I rewrite it pi.q. Dot product is an expectation when one of the components is a distribution. And I will write for a value function v, pv, as the expectation according to the transition kernel of the value function in the next state. So this is the expectation of the Q value according to the policy, and this is the expectation of a value function according to the transition. And with this notation, you can just write the Bellman operator as t pi q as equal to r plus gamma p times the value. The value is pi.q. And the greedy policy, when you maximize component-wise the Q value, you can see it as maximizing over the policy, all the stochastic policy of pi.q, because to maximize this quantity, you have to put all your probability mass on the greedy action. And with this notation, we can write quite simply the entropy and the Kullback-Leibler divergence. So the entropy is defined as the minus the expectation according to the distribution of the log of the density of this distribution. And the entropy tells you, so there's a question. Pi.q, do I mean the probability or the log probability for pi.q? Pi.q, log of pi.q. I don't have log of pi.q. I'll have log of phi and log of q. There's a question indeed to the panelists that over attendee maybe not see. So I will come back later if it's not clear.
Okay, thank you.
Yes?
No, sorry, I said thank you.
So the entropy will tell you how deterministic is your policy somehow. And the Kullback-Leibler divergence is the expectation according to the first policy of the log of the ratio between policies, which is the difference between the log policies. And this will tell you how different are the distribution. And using this notation, we can just write approximate value iteration as follows. And this is what I will modify after. So the policy, the next policy is greedy according to qk. So I have pi.qk. And qk plus 1 is the rho plus gamma p time pi k plus 1.qk. So you see also here that what you optimize for in the greedy step is what you bootstrap in the evaluation step. And this will play a role after. So now we'll see how we can perform regularization on the greedy step. So first we'll see the case where there's no regularization. So here, this is a simplex. So this is a policy for a single state and for three actions. So I need to have things that sum up to 1, being between 0 and 1, so I have a simplex. And in all case, my initial policy will be the uniform policy. So if you do classic greedy policy, you will all your policy will be in a corner of the simplex, because assuming that all Q value are different, the action have different values, but you will be in a corner of the simplex. Now you can add some entropy regularization. So it says that you want to maximize the Q value. You want the policy that will maximize the Q value, but you don't want your policy to be too deterministic. You want your policy to be stochastic enough. So what it tells is that you will compute the red point will be the solution without regularization. And instead of taking the red point, you will take the green point, which will be something between the greedy policy and the uniform policy, because the uniform policy maximizes stochasticity or maximizes entropy. And next, for the next policy, you do the same thing, and you will take better policy, but while remaining close to the center of the simplex. We can also use Kullback-Leibler regularization, and here the idea is that I want to be greedy according to QK, but I don't want to move too much from the previous policy. So for the first step is the same as before because the initial policy is uniform. But for the second step, instead of saying I don't want to deviate too far from the uniform one, you will say I don't want to deviate too far from the previous one by one, and so on. And you can combine both because for many reasons that I will explain later. Another way is to do regularization with the Q values. So this is a bit less usual, but this is heavily linked to Kullback-Leibler regularization. We'll see why. And the idea, instead of being greedy according to the last Q function, you're greedy according to the sum of all past Q functions. So what is the rationale for doing so? Assume that your Q function, Qk, is the optimal Q function plus some noise, and that this noise is zero mean IID, which is not the case, but imagine that it's the case. If you're greedy according to the last Q value, then you will never converge to the optimal policy because you will suffer the noise at each step. But if you're greedy according to the sum of all past Q value, this noise will cancel out because you average a zero mean noise, IID, and so on. And then you would converge to the optimal policy. So things are a bit more complicated in reinforcement learning because you don't have things as simple as this. But this is roughly the idea and why it works. And second, the question is, if we change the greedy step, should we change the evaluation step? So the naive approach is to say, no, I just keep my evaluation step. So I modify with whatever regularization here the greedy step, but I keep the evaluation step as it is. And this is a quite usual approach in the literature, and it's called the type 2 in my own nomenclature. But it's not the right thing to do for many reasons. And the thing is that here, when you do value iteration, what you optimize for is what you bootstrap. So if you modify what you optimize for in the greedy step, you should modify the evaluation step accordingly to bootstrap what you have optimized in the previous step. So this is called type 2. It's probably less usual in the literature, but it's more funded. And practically, it's not costly to do it. It's not more complicated than ignoring the regularization in the evaluation step. So we end up with two kinds of general regularization scheme for approximate dynamic, approximate value iteration here. It's mirror descent VI value iteration type 1 and 2, depending on the regularization of the evaluation step or not. And it's called mirror descent because it's reminiscent of the mirror descent approach in optimization, in the sense that you can see QK as a kind of gradient of the policy. It's not formally the gradient of the policy, but it's like a gradient of a policy because it gives a direction of improvement. And instead of being too greedy, instead of following too much the gradient, you will put some penalization, and that's what mirror descent does in optimization. So we'll do a case study with entropy regularization, and we'll see how to go from this TP scheme. So I will consider type 1, sorry, for the remaining of the talk. And so we have modified a value iteration, adding an entropic term, and we'll see how to derive a DQN-like algorithm and how to also derive a continuous action actor critique. So the approach is really the same as for going from a value iteration to DQN. And we'll study also the theoretical guarantees. So we have the greedy step. The first thing to do is to know if we have an analytical solution for this greedy step. Without entropy, is just I take the action but maximize the Q value. But here, what we have is that the negative entropy, or the entropy is a concave function of the policy, which means that this optimization problem has a single optimum. And this is indeed a Legendre-Fenchel transform, or a convex conjugate, which is a useful tool in optimization. And we know, generally speaking, for any convex function omega, that the convex conjugate is defined as omega star as the max of pi dot q minus omega of pi. And we know that the maximizer is the gradient of the convex conjugate. And there are many useful other properties on Legendre-Fenchel transform. So with negative entropy, the convex conjugate is a log sum x and the maximizer is a softmax, which means that your policy is simply softmax according to qk over tau. And the maximizer is tau log. So here I write a dot product of 1 exponential of qk over tau. It's the tau log the sum over action of the exponential of qk of s action over tau. And this is a soft maximum in the sense that when the temperature goes to 0, this quantity will converge to the maximum of our actions. So it's a smooth maximum, and the softmax is indeed a smooth arc maximum. So we get readily an algorithm because we know that the solution to this is a softmax, and we can compute the softmax as we have analytically as we have discrete actions. And it's the same approach as for DQN. We just modify the loss. So the loss is based on the evaluation step, and we have in addition the entropy. So the entropy is it should be a pi k plus 1 here. That's a typo, and it's pi k plus 1 dot minus tau log pi k plus 1. So I just end up with this red term in addition. And you change the policy. Instead of being greedy, it's now a softmax of the target network over 2. And that's it. So it's a super simple modification of DQN. If you have a DQN running, it's a matter of a few lines of code to change, and you get a soft DQN algorithm. And we get DQN back as the temperature goes to 0. We can write it differently. By the Legendre-Fenchel transform, we know that what we propagate is exactly this quantity. This is what we bootstrap in the evaluation step. So instead of writing pi k plus 1 dot qk plus the entropy of pi k plus 1, we can directly use tau log sum x of qk over 2. And here we have a pure value-based soft DQN version, where instead of having maximum over action, we have a smooth maximum over action, but otherwise it's the same. And again, we obtain DQN back when the temperature goes to 0. So soft DQN doesn't really work better than DQN, as far as I can tell. But it's pretty interesting for continuous actions because this gives rise to one of the state-of-the-art actor critiques. So we still have the greedy step is a solution, the maximizer of the Legendre-Fenchel transform. But in this case, we cannot compute the policy analytically because if we have continuous action, the softmax will involve computing the integral over action of the Q value, which is not tractable in general. So if we cannot compute it analytically, what we can do is that we can do as for the evaluation step, that is put some approximation and learn it using a neural network. So we add before a critique, the Q function, and now we can add an actor, which is a policy. So first solution is quite direct. Here you have the expectation according to the policy of Q value minus tau log policy. So the inside expectation for a given state is really pi.qk plus tau entropy. But I will parameterize my policy by a parameter. It's a neural network, for example, Gaussian policy. And I will put an expectation over states. This expectation is whatever states I have currently in my dataset. And then we want to optimize over the parameters of the policy to maximize for this objective function. And one way to do this is to use importer sampling, because here we have the problem is that we want to optimize for what is inside the expectation, and we cannot compute this expectation because it would involve an integral. So we can do the expectation according to an old network, and then correct with importer sampling to have the same thing, and then we can compute the gradient of this quantity. An alternative to importer sampling is to use the parameterization trick that I will not present into details here, but basically, when the idea is really that when you have a Gaussian policy, say of min mu and variance sigma square, you can say that it's equal to mu plus sigma times epsilon, with epsilon being zero mean Gaussian. And you can use this to have a more tractable optimization problem. The second solution is equivalent, and it's how it's presented in the literature. We know attentively that the policy is softmax according to qk over tau. And instead of optimizing for this loss function that correspond directly to the optimization, the starting optimization program, you can say, well, I want to have the policy pi omega that approximate the best possibly the softmax of qk over tau. And because the Kullback-Leibler in this sense, you get rid of the partition function, and you end up with basically the same optimization problem. So you have an actor loss that will tell you, given a Q network, how to optimize the policy. And then you want to have a loss for the critic. And the loss for the critic is, as before, the same as for DQN, but taking into account the fact that you use continuous actions, so the expectation needs to be sampled, no. And you add entropy term here because you consider regularization in the evaluation step 2. And this is not written in the slide, it should be. This is exactly the soft actor critic algorithm that has been proposed a few years ago, and this, which is roughly one of the state-of-the-art algorithm for continuous actions. And we can do some theoretical analysis when the gradient step is exact. So this doesn't apply to SAC, but it does apply to soft DQN. And we just do as before, that is, we write the dynamic programming scheme. We say that we do some error in the evaluation step, and we can study the propagation of errors. And what we get is exactly the same bound as for DQN, or value iteration. The difference is that instead of converging to the optimal Q function, you would converge to a biased optimal Q function, because you have a regularization term that tells, I want to be optimal, but I don't want to go too far from the uniform policy. And because of this, you cannot really, this regularization term doesn't vanish asymptotically, so you cannot converge to a deterministic policy by saying I want to remain a bit stochastic. So you have a bias, and otherwise the bound is the same. So regarding the propagation of errors, there's no advantage, but there are other arguments. And the arguments are for exploration. Because you favor a stochastic policy, you will have a better exploration. You have arguments regarding the optimization landscape. And the reason is that if you look pi k plus 1 as a function of pi or of qk, without regularization, it's not a smooth function. but the softmax is a smooth function. A smooth in the sense that your greedy operator will be Lipschitz, which is not when you take the argmax or the hard greedy step. So because you get this smoothness, you improve the optimization landscape and it's easier to learn. Now we will have a look at Kullback-Lagerberg regularization. So maybe there are some questions so far before I continue.
Okay, so there is two questions. So one by Ashraf. In regularization, why is it a good idea to have a policy close to the uniform one, or in other words, very stochastic?
So there are many reasons. One reason is to have a policy that do enough exploration, and it was before all used in actor critic algorithm, where by the way you compute stochastic policy. So if your policy is more stochastic, it will perform a better exploration. And another reason is to have Lipschitz greedy step, which will smooth the optimization landscape and ease the learning of the neural networks.
Thank you. The other question is actually a bibliographic question. So it's for having some references for that, but I guess you may provide some afterwards, right?
Yeah, there are plenty of references in the slides.
Okay, thank you.
And I think the slides will be available. I can make them available. Otherwise, there's a paper called A Theory of Regularized Markov Decision Processes, and there are many references in it. And another one, which is called Leverage the Average, an analysis of Kullback-Lagerberg regularization in reinforcement learning. And this one provides a lot of pointers too. But everything is in the slides that will be available.
Perfect. So we have other questions. I don't know if you want to move on or as you prefer.
Last question.
Okay. So let me take the question from Richard. So do we retrieve a policy close to the optimal one if we take the greedy action from your regularized queue?
Sorry, didn't get it.
So I guess, so Richard, so the question is, do we retrieve a policy close to the optimal one? So I guess without regularization, if we take the greedy action from your regularized queue.
That's a good question indeed. It might not be the case. It depends on the MDP and the amount of regularization. It would be really good to say that, well, I put any quantity of regularization, it will help me, and in the end, I just output the greedy policy instead of the softmax, and how to have the best policy. But no, it's not that easy, and it really depends on the MDP and the amount of regularization. And I have some counterexamples.
Great, thank you.
Thanks. So I'll continue with Kullback-Lagerberg regularization. So the same thing as before, but now we will put a KL term instead of entropy term. And here again, the approach will be the same. So now if we look at the greedy step, instead of having the entropy, we have the Kullback-Lagerberg. And it's again a Legendre function transform as before. And we can show, it's a classical result, that the new policy will be proportional to the old policy time exponential of qk over lambda. So you can think about this as a kind of weighted softmax. And if you use a direct induction argument, what you can show is that pi k itself is proportional to pi k minus 1 time exponential of qk minus 1. So pi k plus 1 will be proportional to pi k minus 1 exponential the sum of the two past q values. So if you iterate this argument, it will be softmax according to the sum of all past q values. So this is linked to the regularization with q values that I talked about before. And we can write this DP scheme equivalently by saying that the evaluation step is the same as before. I didn't change how I evolve my Q value, but in addition, I will average my Q values over time. So this is HK is just the average of all past Q values. And I would say that my greedy policy, my sub-greedy policy, will be softmax according to the sum of Q values, or to HK plus 1, putting the right regularization factor. And these two are really equivalent. And this form is used for the analysis, and both forms can be used to derive algorithm. So now, if you look at practical algorithm, here we have an issue, because even with discrete actions, the policy should be learned. So I will just go back one slide. The thing is that you want to have this quantity, basically. So ever you remember the past policy and you can do something, but it will require remembering all past policy, and it can be difficult. But what you can do is to say the sum of Q value. And if your Q function is linearly parameterized, that is QK is theta transpose a feature vector, you can just average the past parameters. But if you work with deep network, it doesn't work anymore. So the solution, the first solution is to add an actor or policy network to approximate what's going on. And we can do as before, except that instead of considering the entropy, we consider the Kullback-Leibler divergence. So we have the previous policy. So we have a target network for the policy, and for in addition to having a target network for the critic, for the Q value. And we can just rewrite this abstract optimization problem into a deep learning optimization problem, and maximize for this over the parameter omega, and use the same tricks as before. That is, ever we have discrete actions and we can do things analytic, we can just write the sum. Or if we have continuous action, we should rely to ever import a sampling, or to the reparameterization trick. And there are many different options to get a tractable approximation of this optimization problem. And another solution is to approximate the average of Q values, so the H that we had before. This was a real average of past Q values, but a real average is not practical in the deep learning setting, but we can do a moving average of past Q values. So here, basically, I say that H omega should be close to 1 minus alpha times the old H plus alpha times the new Q, and be soft greedy according to H omega. And these are two kinds of policies, one direct and one indirect through the sum of Q values. And we can do the evaluation step as before by adding the new component into all loss and optimizing for it. Now we have, regarding the theoretical analysis, we have a really nice bound for this scheme. When there's no approximation error in the greedy step. That is, when you can really compute the next policy exactly. And this is important for the bound to all. So on the right-hand side, I recall the bound for approximate value iteration. So we bound the difference between the optimal Q function and the Q function of the computed policy by a square horizon term, moving average of the norm of the error and the convergence rate. And if you look at what kind of bound we can obtain with regularized value iteration, with the Kullback-Leibler divergence, here, instead of having a square horizon dependency, we have only a linear horizon dependency. And this is really super strong. This cannot be improved as far as I know. And when this guy is usually of the order of 100, gaining a square is really something interesting. And something even more interesting is that instead of having the sum of the norm of the error, we have the norm of the sum of the error. This means that you can have a compensation of errors between iterations. And if your error is zero mean, this, by the law of large numbers, will converge to 0. Which means that you can make your value iteration with approximation converging, even if you're bad at each iteration, as long as your error are 0 mean, which is a sensible assumption in many cases. And regarding the convergence rate, we have a smaller convergence rate. We have 1 over k instead of gamma power k. So without error, it's not worth doing regularization because you will just converge, the convergence will be slower. But it is also to be expected because when you do kernel regularization, you say, I want to compute the greedy policy, but I don't want to move too far from the current policy. So you will go, the convergence cannot be faster. And if you look at this small empirical example, in blue, you have approximate value iteration. So here you have, it's an example where the error is really 0 mean and not IID because, but it's a martingale. So it can converge to 0 if you average. So if you do value iteration, it doesn't converge to 0. It cannot converge to 0. But as soon as you put some Kullback-Leibler regularization, and the different curves are for different value of lambda, then you will converge to the optimal policy by design somehow. So this is the next slide, is just a single slide to show the many ways to do regularization. You can consider only entropy, only Kullback-Leibler, or both, and you can consider type 1 or type 2. And depending on the case, you will retrieve a lot of existing algorithms. And yeah, I won't expand more because if we had 2 hours, I could have spent 1 more hour discussing each of these algorithms and the associated theoretical guarantees. But there's a paper named Reverse the Average, which is within the references, where all of this is explained. And now I will talk about the issue with Kullback-Leibler regularization. The thing is that we have a really super nice bound for Kullback-Leibler regularization, but this bound doesn't hold for deep learning because we do error in the greedy step. So everything relies on this equivalence. And the proof is based on this DP scheme. But the thing is that because we cannot compute analytically when pi k is a neural network and qk is a neural network, we cannot compute analytically this. So we do error in the greedy step. So we could say, well, no problem. I will start with this. I can compute the softmax according to hk because if I have discrete actions, at least I can compute the softmax analytically. But we cannot do the true average with neural networks, except if we remember all past neural networks, and it's usually too expensive. So we lost the equivalence, and we cannot do this with stochastic approximation. And the moving averaging approach I presented just before is an approximation to this. And a remedy to this is Munchausen Reinforcement Learning, which is a pretty very simple trick, but super efficient. So here, I write generally a value iteration with both Kullback-Leibler and entropy regularization. This is equivalent to putting a lambda here and a tau here. You have a bijection. And what you can show is that if you replace Q by Q prime plus alpha tau log the policy, so by just doing a kind of writing of the DP scheme, you no longer estimate the true Q function, but something which is the Q function plus the tau log policy. You end up with something which is purely equivalent, and where the policy will now be greedy softmax according to the Q value, because you have entropy regularization. You can compute this analytically with discrete actions. Here you have, so if you consider only the blue term, it's just a soft value iteration. But in addition, you add alpha to log the greedy policy, the soft greedy policy. So this is really a sub-value iteration, so only with entropy, and you bootstrap the policy, which give you some knowledge about what would be the good action to reinforce. And this is what we call the Munchausen term. And as a bonus, a good thing is that it also increases the action gap compared to doing this, because these two schemes will give the same sequence of policies, but they won't give the same sequence of Q values. The sequence of Q value will be linked by this relation. And the thing is that the Q thing that you compute here has an action gap. The action gap is the difference for a given state between the maximizing action and the second best action. And this is very important, because the smaller the action gap is, the harder it will be to distinguish between the best action and the second best. And here, basically, you have alpha that should be between 0 and 1, and you will increase the gap by multiplying the original gap by 1/1 minus alpha. And in the limit, if you take alpha equal to 1, you have an infinite action gap, which is theoretically true, but numerically unstable. And if we go back to our case study on DQN, we can modify DQN with the Munchausen term to get Munchausen DQN. So we only modify the regression target of DQN. So this is the DQN update. And here I just write the Q hat DQN is the target of the elder regression problem, L2 regression problem. So this is DQN. You compute rho plus gamma, the expectation according to the policy of Q theta bar, with P theta bar being really according to Q theta bar. So this is the max overaction indeed. We need the stochastic policy, so we add some entropy regularization. So this is what we did before to get soft DQN. And then we just add the Munchausen term. And the Munchausen term is just the scaled up policy. The policy being softmax according to the target Q function. And that's it. And so it's really a super simple modification of DQN. It's again, if you have sub DQN, it's a matter of number of car rather than line of code. And the thing is, it works super well. So here I show result on Atari. So you have the 60 Atari games. I think Bilal presented them before. And these are the aggregated results. On the left, you have the mean score over games, and on the right, the normalized score. And it's human normalized, so it's how much better to human it is. And you have DQN in orange. You have C51 in green. So I don't know if it was presented before, but C51 is a distributional reinforcement learning algorithm, way better than DQN. And with a much more complicated loss, a much more complicated architecture, network architecture, and so on. And here you have Munchausen DQN. Munchausen DQN do way better than DQN and also even better than C51, both in mean and median. And the thing is that the difference with DQN is just this additional term. So it's really super simple, but it's super efficient. And the thing is that the bound I provided before on the performance bound on the Kullback-Leibler divergence apply to this algorithm, even if we consider deep networks and so on. Here you can see the improvement per game. So it works well. And the thing is that it's quite general. And as an example, we apply it to IQN. So IQN is probably the state of the art, or was until very recently, distributional reinforcement learning algorithm. So it's basically similar to C51, except that the way the distributional aspect is considered is a bit different. It works very well, but we can apply the Munchausen ID to this. So the theory probably does not hold in this case because the setting is different. The distribution of reinforcement learning, instead of considering the expectation of the cumulative reward, you look at the cumulative reward without expectation, and you try to learn the distribution instead of learning the value. But you can apply the algorithmic ID readily to this algorithm, and you can combine the Munchausen ID with IQN, and again, it improves a lot compared to the original IQN, and it even goes over Rainbow that combines many tricks like C51, double Q-learning, and step returns, and so on and so on. So by just adding the Munchausen term, we can earn a lot. And that's it on time. So in this talk, I've provided regularization, an overview of regularized approximate dynamic programming. There are very interesting connections to convex optimization and online learning, because the kind of things we've seen are linked to mirror descent or follow the regularized leader or dual averaging, these kind of things. But it's not as simple as framing the reinforcement learning as an optimization problem, especially regarding the theoretical part. It's more a kind of abstract connection. And with using this viewpoint, we can go over many different reinforcement learning agents and analyze them. And there are many other possible outcomes for regularization in general, and notably regarding imitation learning, inverse reinforcement learning, offline reinforcement learning, or game theory, and so on and so on. So I think I have a few minutes to take additional questions. Thank you for your attention.
So thank you, Matthieu. Thank you very much for this nice talk with very promising results. So we have indeed several questions, so I might subsample from this question. So there is a practice related question. So in practice, how to choose tau, lambda, and alpha? So the tuning, the parameter tuning question.
That's a good question. So for alpha, so if you take Munchausen, the last thing, usually speaking, it's a matter of searching parameters for it might be the problem dependent and so on. But if you take Munchausen reinforcement learning, the thing is to take alpha close to 1, but not too close to 1, because you want theoretically to take alpha as big as possible, because you want to increase the action gap. But at the same time, if you increase it too much, you will try to estimate the kind of Q value that will be the optimal value for optimal action and minus infinity for suboptimal action. And it can be numerically unstable. So if you take, say, 0.9, it will work well. And regarding the temperature, taking a small temperature is usually fine with discrete actions. The Munchausen ID doesn't apply well to the continuous action setting, because it requires having an exact ready step, and if you have continuous action, you cannot compute the softmax and so on. And if you look at the temperature for soft actor critic, what they do is that they have an additional loss for learning the temperature, and instead of saying I want this temperature, they use target entropy. So they say I want my final entropy to be this level, and this level is how stochastic would be the final policy be. And so you have a kind of automatic scheduling of the temperature through this loss. So there are many different options and some automated one.
Thanks for Kimon. So maybe I will combine several questions in one question. So these are about replacing the mirror descent by something else. So is there a way to replace mirror descent with a Newton step, for example, or with Adagrad to get better bounds? There is another question about, can we imagine some momentum-based method to speed up convergence? And I also have a question about, can we just change the regularizer as for classical mirror descent results? So all those questions.
Okay, so this is a very interesting question and a very difficult one. So yeah, we can imagine different things. the question is how to frame the algorithm. We tried some things taking inspiration from Adam, for example, and it wasn't working well. You mentioned momentum. We did something inspired by momentum, which is called momentum DQN, where instead of having a moving average of the gradient, you have a moving average of the Q values, but it ends up being a special case of what I presented, but we discovered it after doing the momentum-based step. So I truly think that we can really get inspiration from the optimization iterator to design a new DP scheme. And for example, maybe we can do Nesterov-like things to have a faster convergence or this kind of things. But so the problem is to derive the good thing, because it's not just I have this function and I apply this optimization problem. It's more a kind of it resembles, it looks like, but it's not the same exactly. And regarding the different kind of regularization, so many of the results I've shown hold for any kind of regularization. As long as the big omega is convex, it's fine. For the bound, they are the less interesting, not the one that allow averaging errors. The thing is that you work on the simplex because you work on a density on probability distribution. So the question is, beyond Shannon entropy, what would be interesting? There are some works where they consider, for example, if you work with, instead of taking the Shannon entropy, if you take the L2 distance of the policy, the sum of the square of the probabilities, then you end up with something called the Thalys entropy. And the Thalys entropy is a kind of, it will get guards of a kind of sparse max, in the sense that it looks like the softmax, but some probabilities of actions are put exactly to 0. And it was used to learn policies for very large discrete action space. And some of the theoretical results apply to this case, but not so. The thing is that Shannon and Kullback-Lagrange are the more natural one in the end.
I see. Thank you very much for all these questions, these answers.